Welcome everyone. In this lesson, we're going to start to look at how to find the maximum and minimum values for a multivariable function. And we're going to be primarily looking at the two-variable case. So let's start with the definition. So let's let our function be first of all, a function of two variables, so x and y. And we say that we have a local maximum at the point a, b, if the function value at that point is larger than all of the surrounding function values when we're relatively close to that point AB. And you want to think of this as like a mountain peak. So you want to think of our two-variable function as a surface. And so when we graph our surface, a local maximum would be kind of look like a mountain peak on our surface. Now, a local minimum at a point AB happens if the function value at that point is smaller than all of the kind of surrounding function values when we're relatively near that point AB. And again, this would kind of look like, if we're picturing our surface, our function as a surface, this would be like a valley. This would be a low point on our graph. Now, just a little bit of notation or terminology here. So you want to think of the point AB as kind of like where the max or min happens. So you want to think of that point AB as kind of like the location for where the max or min occurs. And then you want to think of the actual value of our function at that point is the max or min value. So when we kind of say the word value here, that implies that we're actually talking about the function value at that point. And when we're talking about, well, find where the max or min happens, we're really just talking about the location. So we're just actually talking about the coordinates of the point. So just a little bit of terminology there. Now, it's possible that these two inequalities, if we find a point, that these inequalities might hold not only for the points x, y that are close to AB, but it might hold for all of the points in the domain of our function. And if that happens, that's something special. So if the inequalities hold for all points, kind of the key word there, all points in the domain, well then our local max is actually called the absolute max of our function, or the absolute min for our function. So again, if you're kind of thinking of your function, the graph of your function as like a surface that's kind of hovering above the xy plane, a local max would be a kind of a single mountain peak, and the absolute max would be the highest mountain peak. Or if you're talking about an absolute min, it would be the lowest or the deepest valley on your surface. So it's kind of the extreme high point or the extreme low point on your surface. So we call those the absolute max and the absolute min. So it helps with a picture. So here's an example. Here's a function, a two-variable function, and it's kind of hovering above the xy plane. It dips down a little bit at points. And in this graph, we see kind of four local extrema. So let's just label these. And so we see something going on here, 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 and here. So I'm just going to label those points 1, 2, 3, and 4, just so we can know what we're talking about. All right, so what's going on at point 1? Well, point 1 is a local max because imagine kind of standing on your surface. So I'm standing on the surface, and then immediately surrounding that point, it's downhill in all directions. So that's a high point. Same thing at point 2. It's a local max. Because, again, imagine standing on that peak, and if I take a step in any direction, it's downhill. All right, what about point 3? Well, point 3 is a local min. Because if I was standing at this point, way down there, and I took a step in any direction, I'm going uphill. So right around that low point, it's uphill in all directions. So this is as low as I can get right in that immediate area. And then finally, for point 4, also a local min. Same kind of reasoning. Imagine standing down there, and it's uphill in all directions right around that point. All right, so points 1 and 2 are local maxes. Points 3 and 4, we have a local min there. Now, if we're kind of comparing the peaks that happen at points 1 and 2, well, point 1 is not only a local min, but it's an absolute, or not only is it a local max, but it's an absolute max, because that's as high as our surface gets. So if I'm standing up here, this is me on top of Mount Everest. It's downhill everywhere else. Everywhere else is below. Now, if I'm standing on the top of Peak 2, yeah, in the immediate area here, it's downhill in all directions, but eventually there's this other mountain peak where there's points that are higher than it. So point 2 is a local max, but it's not absolute. And same kind of deal with point 3. Point 4 is the lowest my surface ever gets. So all of the other points on the surface are higher than it. So what's going on at point 4 there, that's as low as my surface ever gets. So that is an absolute min. So it's both a local min and an absolute min. And what that means is point 3, yeah, it's a low point, but it's a low point only in that immediate area. If eventually I move away from that low point and I move far enough away, eventually I'll get to kind of other sections of my surface that are actually lower. So it's not an absolute min. All right. A picture kind of helps just to see what's going on. All right, so now we want to see, how do we actually find these high points and low points? And we have a result, a theorem here, and this tells us how to actually kind of go about locating where we might have a max or a min. And it relates to the derivative. And one thing I just want to mention before we actually read through this is this theorem only tells us possible locations for a local max or min. So that's important. It doesn't necessarily mean guarantee that if we find a point that satisfies the conditions here, then we're guaranteed to have a local max or min. But it tells us that if we have a point that satisfies the conditions here, then we might have a max or min. So this kind of gives us all possible locations where we might have a max or min, and then we'll have to do a little bit more work to kind of determine what's going on exactly at those points. So let's read through this. It says, if our function f has a local max or min at the specific points, and the first order partial derivatives of f exist there, then what happens is the partial derivative of x evaluated at that point is equal to 0, and the partial derivative with respect to y evaluated at that point is equal to 0. So the way we're going to use this is we're going to have a function, we're going to calculate the partial derivatives, and then we're going to set the partial derivatives equal to 0 and then solve for x and y. And what that will be, that will tell us where we might have a local max or min. Another way to say this, if the partial derivative of x is 0 and the partial derivative of y is 0, another way to write this is using the gradient. So we might say the gradient of f evaluated at this point AB is equal to the 0 vector. So it's kind of an equivalent way of stating that. And so the proof, won't go through all of it, but we'll kind of go through maybe half of that. And we're really going to rely on what we did in Calc 1, the one variable case. So we're going to suppose that f, let's just suppose f has a local max at the point AB. What we're going to do is there's two parts to this. First part is we're going to keep y fixed. And we're going to let x change by a little bit surrounding that point A. So we're going to cook up a function. And we're going to call this function, let's call it g. So let's let g of x equal the function f of x, and we're going to keep y fixed at b. So we're going to let x change, but we're keeping y fixed. So this is a one variable function. So what happens is we're looking at our function f just in the x direction here. And if we kind of go back, let's suppose that we're standing on our mountain peak and we look, if we're standing on our peak there, it's downhill in both directions. It's downhill in all directions. So in particular, it would be downhill in the x direction. So what that means is if we kind of look just in the x direction, we should have a peak in the one variable case. So if it's a local max in all directions, well then this function should have a local max just in the x direction. So g of x has a max, has a local max at x equals a. This is a one variable function, and we know that our original function f has a max in all directions at that point. So in particular, if we look at just the x direction, it has to be a local max there. And if a one variable function has a local max, well, that means the derivative at that point has to be equal to 0. We have a critical number. And what we're doing with this kind of creative little function here is we're letting x change and we're holding y fixed. And if we do the derivative, we're doing the derivative with respect to x. So we're looking at what happens here if we change x by a little bit while we keep y constant. That's exactly what the partial derivative is. So that means g prime here is actually just the partial derivative with respect to x. Kind of gave it a fancy little name. And we get f partial x at that point is equal to 0. And then you could do something similar for the y direction. And for the y direction, you would kind of cook up a new function. We'll call it h of y. And this one is we're going to keep x fixed, and then we'll change y by, we'll let y change. And we won't go through all of it, but this would show you with some steps similar in the middle, similar reasoning, that the y partial derivative would be 0 there. So this is kind of a clever way to kind of use our Calc 1 result for the one variable case to say if our function has a local max, well then it has to be a local max in the x direction and it has to be a local max in the y direction. Similar for local minimums. All right, so the geometric kind of interpretation of this, very similar to what we did. Again, we're kind of relying on Calc 1 here. So if we were to graph our surface, the graph of our surface has a horizontal tangent plane wherever we have a local max or a local min. And the way to kind of prove this is if we write down the equation of our tangent plane, this is something we looked at. It's z minus the z coordinate is equal to our x partial evaluated at the point AB times x minus a plus the y partial evaluated at the point AB times y minus b. And if we have a local max or a local min, well, what has to happen then is our x partial and our y partial, they both have to be 0. So these are both equal to 0. And if that's the case, then this whole piece is gone and this whole piece is gone, and we can just get z minus our z coordinate is equal to 0, and we end up with z is equal to just a constant. So that's a horizontal plane. So you want to keep this in mind. You know, when we were doing Calc 1, what did we have? We didn't have a horizontal tangent plane, but we had a horizontal tangent line. Same idea. When we had a high point on our graph, we had a tangent line or a horizontal tangent line. Or when we had a low point on our graph, horizontal tangent line. Now in the two variable case, now we're having horizontal tangent planes. And so we're going to be trying to find these points A, B, where the partial derivative of x is equal to 0 at that point, and the partial derivative with respect to y is equal to 0 at that point. And we're going to call these locations critical points of our function. Sometimes we might get into the case where the partial derivative does not exist. So we might be looking for where the derivative might not exist. But primarily we're going to be looking at where do these partial derivatives both equal 0. So again, these are the only possible locations for a max or min. They can't happen, a max or min can't happen anywhere else. It can only happen at the places where both partial derivatives are 0. But unfortunately, not every critical number or not every critical point is going to be a max or min. So there's sometimes critical points that are neither max nor min. But at least we are going to be able to identify if our function does have a max or min, it can only happen at a critical point. All right, so let's try an example. We're going to look at example 1. So we're going to find the critical points for this function x squared plus y squared minus 2x minus 6y plus 14. So what we're going to do, step 1, let's get both of our partial derivatives. So we want to get f partial x and f partial y. So f partial x, this function's not too bad. Let's go through it. Derivative of x squared is 2x, and then the y terms, there's no x's there, so they differentiate to 0. Constant differentiates to 0, and then we have minus 2. So our x partial is 2x minus 2. And then our y partial, again, let's go through. x terms differentiate to 0, 14 differentiates to 0, and then we're going to have 2y minus 6. All right, so we find both partial derivatives, and then the second step is we set both of them equal to 0. So we're going to have to solve both of these equations simultaneously. So we get 0 is equal to 2x minus 2, and then 0 is equal to 2y minus 6. And then you solve. And that's generally the trickiest part, is you solve these equations for x and y. And now this is our first example, so this one's not going to be too bad. This first equation, we can just do a direct solve. And we get x is equal to 1. And same thing over here. We can just do a direct solve here, and we get y is equal to 3. So sometimes you might have to work with the first equation, maybe solve for x and y, and then you have to plug it into the second equation, and then you have to solve that one, and then you got to go back over here. And we'll see more complicated examples. Right now, we're just kind of starting off easy, where we get these two equations that we can just solve on their own. And so then you put the x and y values together, and we have our critical point. So our critical point here is the point 1, 3. And what we're going to see is this is the only spot where we might have a max or a min. It doesn't tell us what we have there, but it tells us if we are going to have a max or a min, it has to happen at that point. So what we're going to see is that there's ways to kind of classify or to test what's going on at a critical point. And we're going to use what's called the second derivative test. And this tells us, this second derivative test is going to tell us what's going on at this point. Do we have a max? Do we have a min? Do we have something else? Who knows? So we're going to see that next time. So we'll see you then. Bye-bye.